So is everyone able to see my presentation clearly?
Yes.
Okay, cool. So let's get started. So good evening, everyone. So today I want to take you deeper into what a digital design is and the fascinating world of logic synthesis. So just imagine like you're going to architect a cutting edge smartphone, or like these days you're building the data center chips and everything. So the challenge here is to design the brain, the processor, or the application processor, ensuring that it's not just powerful, but also efficient and energy conscious, right? So how is this course designed? As in, I know this is just a demo class, but who is this course designed for? So mainly the new college grads, both bachelors as well as masters, and engineers from different backgrounds, particularly with ASIC design. Like you have people in the logic design, you have in verification, you have people in the backend, which is STA, sign off, and all that. So this is for all those engineers from different ASIC background itself. Also the engineers in like embedded and other people. And for college students, as in people who are in their final year of graduation, so they can as well take this course, and it is like that simple to understand. And all the VLSI enthusiasts and people who are not happy with their current career path as well. Okay, so this is who I am. My name is Vamsi, and I have almost like 12 to 13 years of experience in the semiconductor industry. And I've been teaching for a while. It's a hobby and I love teaching. So I've helped hundreds of engineers and thousands of students. I work at multiple companies. So I work for Broadcom, Cisco, MediaTek, Microsoft. And this is where you can reach me out. Okay, so let's start with the basics, right? So first of all, before even going into synthesis, let's try to understand the basics. So in digital design, we basically work with the basic building blocks called the logic gates, right? And I assume that everyone over here do understand what AND gates, OR gates, and NOT gates are. So these gates basically operate on the binary values, zeros and ones. And if you see here, I have put up NAND gate, NOT gate, like which are again built up on top of our basic AND, OR, and NOT gates, right? The exclusive OR and exclusive NOR. But how do we make sense of these gates in a larger context, right? So everyone understand the gates, but how are they used, and in a larger context, like what exactly do they imply? So that is where this Boolean algebra comes into the picture, the whole mathematical foundation of the digital design. So that is what I try to show on the right. So this is basically some mathematical functions which can be implied using the gates that I've shown on the left. Right. So the Boolean algebra is nothing but a relationship between your inputs and outputs. So you have you give some inputs, you have a circuit, it takes those inputs and it generates some outputs from that. So that is the basic concept of the Boolean algebra. Right. So all our digital systems, or like the chips that we do, are all based on this Boolean algebra itself. Of course, you don't see it at that level. All you see is some circuit connections, and those circuits in turn perform the same thing, the intended Boolean algebra. Right? Sorry,
Just
I
continue,
didn't hear you.
You can continue.
Okay, sure. So moving on to, right, like why do we really need logical synthesis? Like, what is the need for logical synthesis? So designing large scale digital circuits, right, manually is like trying to build a complex structure with bare hands. It is definitely not possible because it's time consuming. See, once upon a time, like when the whole concept of this circuit design, everything started, the chips used to be pretty small and people used to really design that using hands. But nowadays, you have billions of transistors, you have millions of gates, millions and billions of gates, which is practically impossible for a human to do with their hands. The main reason is like time consuming, it is also error prone and definitely not scalable, right? So that is where this whole concept of logic synthesis comes into picture. It it is really an art of transforming a higher level description language or the HDL language, right, into a netlist. So netlist is nothing but the logical gates. So I mean, I have just a sample, simple code snippet on the right. So wherein the one you see on the top where you have the module definition. So it is basically taking some inputs which are A, B, C, D, and giving an output X. So how are those inputs related to the output is defined by this assign statement, assign X equals A and B or A and C or A and D. So this is basically the Boolean algebra that we have seen previously, right? So this is written using a HDL or a hardware description language. Generally, like people use Verilog, VHDL, or the system Verilog, basically. So, and that is finally, after your logical synthesis is done, is converted into the format you see below, which is where like you still have the module. Basically, all the AND functions or the OR functions is converted into the equivalent gates. So here you see wire, which is nothing but your regular wire connections between different gates. And you see something called INVX1, OAI 21X1 or 2X2, right? Like those are nothing but your technology gates or your inverter AND gates, OR gates, some complex combinational gates and all that. So which shows like what are the inputs and what are the outputs for that. Correct? So in order to bridge the gap between our design and the physical implementation, that is where this logical synthesis comes into picture. So if you see the overall design flow, right, like the VLSI design flow, how it is. So on the left, like you see, right, the complete design flow, you start with the system specification, which is nothing but your algorithm. And from that system specification, you design your architecture, like how the chip architecture should be. And followed by the chip architecture, you do the high level synthesis. Followed by that, you do logical synthesis. High level synthesis is where like you code it using the HDL, and that using the logical synthesis, you convert that HDL into the final netlist, which has all your technology gates and everything. So from the logical synthesis, you go to the physical design, wherein you take the netlist from the logical synthesis and do the implementation, actual physical implementation, wherein you have a fixed chip size or the die size, and you try to place the gates and everything. You try to meet timing, you try to meet, there are like a lot of parameters like which you try to meet. I'll go into them in the next slides, right? So followed by that, once your implementation is done, once you meet your all your design parameters, you give that design to the fabrication. So basically, like TSMC, as you all know, is one of the biggest fabrication house. So they do the fabrication of the chip, and then the chip is packaged, and the testing of the chip happens. So those are all the various stages. That's how the complete design flow is. So that is what I have shown in order to understand this flow clearly, right? Like I just shown it in the second picture here. it starts with an algorithm that is nothing but your system specification. See here, it's a simple algorithm wherein I just wrote a small loop for I equals 0, I equal 15. Sum is sum plus data of I. So it takes each data and it keeps adding it to the sum. So that's a simple algorithm, but in reality, the algorithms will be pretty complex, not as simple as this. So you take that algorithm and convert into an architecture. So I also showed something called as a technology dependent, right? So generally when you write an algorithm, it has nothing to do anything with the technology. Technology nodes, people are working on 7 nanometer technology nodes, 5 nanometer, 3 nanometer technology nodes and everything. So for you to write an algo, it has nothing to do with the technology, right? But when it comes to architecture, it is 10% technology dependent. It is not completely technology dependent, but it still has some technology dependence in the sense that you have to keep in mind, like what are the boundaries or what are the limitations of the technology, and based on that only you can come up with the architecture. So that is where that 10% technology dependent thing comes in. Then you write your behavioral synthesis, which is nothing but, like I said, the high level synthesis, right? So you convert that architecture into your HDL code. So that is also like 20% technology dependent. Like I said, like you have to understand the nuances of the technology or the limitations of the technology in order to, or the leverage that the technology, because from technology to technology, sometimes like you have the standard cells, you have the gates which are much faster. Maybe as you go to a lower technology node, the gates are becoming faster. So using that, you can, the way you write your HDL code also changes, right? So that is where your RTL comes in. RTL is nothing but the register transport level. So you take that HDL code or the RTL and do the logic synthesis. So this is the main topic of today. So in the logic synthesis, you take that RTL code and convert into the gate level. This is where it is 100% technology dependent, as in once you convert that code into the gates, the one that you see here as INV X1 or the inverter gate or gate. So these are all dependent on the technology. You have a library coming from the foundry or the library for the technology, which has all the gates, what are the delays, what are the loads, what are the fan out and everything. So based on that, the logical synthesis tool optimizes the RTL code and comes up with the final netlist. Sorry, was there a question for me? Okay. So the tools of trade, right? So when you're doing logical synthesis, not just understanding your concepts, but you also have to know like what are the tools that are widely used, right? So I've listed just tools. I've listed the tools from just 2 companies here, but there are other tools, but these 2 are. Hello?
Sir, hello?
Yeah.
But actually, what happens at the register level, sir, if you can repeat the steps which you told? At the register level, what does it happen?
Okay, so register level is where you first define the architecture, right? Like, okay, let's say you have a chip. You define saying, okay, this is how much memory that I should have in my chip. This is the processor, and this is how my chip interacts with the outside world, as in the IOs, right? How you get the signals to your chip and how the signals from the chip transfer to your board. So all these things is defined by your architecture. Once you have that architecture, how do you convert that architecture into a code, right? Like you write your Verilog, or like I said, system Verilog people use, or the VSTL, using which you convert that into a code. That is nothing but your register level.
Yes, sir. Yes, sir. Okay.
Yeah.
Thank you.
So logical synthesis takes that RTL code, RTL or the VHDL code or the Verilog code and converts into a gate level netlist. Okay, so the gate level netlist is nothing but it's a Verilog wherein you have all your gates coming in. Instead of having a code, something like X equals A and B or A and C or A and D, you have the actual gates coming in, like the inverters or gates, AND gates, etc. Okay, so coming to the tools of trade, like I said, these two companies are leading in providing the tools for synthesis. There are many other players as well, like the Mentor Graphics and other companies, but I have not listed them here. But these are pretty widely used tools for synthesis. So when it comes to Synopsys, you have something called as a DC or design compiler, and you also have the Fusion compiler. So these are the two tools that are used in the industry, along with this Cadence, who have this tool called Genus, and that is also very widely used in the industry. So these are the two tools like you use to do the logic synthesis. Like I said, right, like some things, the tools are smart in doing some things, as in to optimize the gates better with such a huge designs, like millions of gates and everything. It's not possible for a human to really write the Boolean equations and interpret what is the final optimized design and all. So, okay, coming to the logic synthesis. So what are the inputs and what are the output formats? So these are the inputs that you generally require. The timing libraries in Liberty format or the .lib. When you have different formats being used across different tools, but generally it's a .lib. Some tools use something called as a NDM as well, and those are nothing but your timing libraries. So timing libraries have your all the gates defined, like I said, what are the delay for a particular load and all that. So all this information is part of the timing libraries. The next one is the RTL and Verilog or other HDL languages. Like I said, like you have the VHDL code or the Verilog code, that is also an input for your logical synthesis. Timing constraints in the form of an SDC file. So what are timing constraints, right? So let's say I have a design. I can't just take the design blindly and convert that into gates like how I want, right? There are some set of constraints to which that particular design is bounded to. As in, I define the throughput. Like from the time I get the input and it does the logical calculations and it generates the output, I need all this to happen within, let's say, 2ns, just for an example sake, right? So that's a constraint. So the throughput for that should be like 2ns, as in the latency for that design. Like that, you have multiple constraints. I mean, once we go deeper into what the constraints are and how the constraints can be written, you will understand pretty very well. But for now, just understand that every design is subjected to some constraints, and you have to adhere to those constraints and see that you meet your QR or the design requirements, right? Sorry, I mean, this is a typo, but so going to the outputs, right? Like I said, we have the gate level netlist that is generated. And though you give the constraints as an input, you also write the constraints as an output. The reason being, this design after logical synthesis is taken into physical implementation, or also called as a PNR, right? Even for the physical implementation, you still have the constraints. Your design still have to adhere to those constraints that you've used in logical synthesis. So that is the reason some people like write out SDC after your synthesis as well and use that as an input for the next stage. Scanf. So sometimes like we do a scan chain insertion as part of logical synthesis. like I said, I'll explain what a scanf is and what is the scan chain and everything as we delve deeper into the course. But for now, just understand that scan chain is something that we insert in order to test our chip. So that is something that happens during logical synthesis, or like some people do it after logical synthesis happens. It varies, but if you have done that, you will have a scanf that is written out. And the final thing is the reports, right? Like since you have done the synthesis, you write out the reports to analyze whether you are meeting your design constraints or not. Okay, like I said, what are the requirements, right? Like when you're synthesizing your design, what are your main motivation and goals? First of all, for synthesis, the main motivation is the fewer bugs and improved productivity. As in, like, any manual thing is prone to mistakes or errors, right? But tools are so automated that you will end up with very few bugs. It's not that it is not error prone. Even there could be some errors or some mistakes that happen with the tools, but it crunches a lot of data that and gives it in a format that user can look into it and debug those bugs or errors, right? But it definitely improves the productivity. For you, if it take like 30 days, maybe it will do within like 30 minutes or 1 hour, right? And the second thing is the same HDL or the VHDL code or the Verilog code can be implemented across different technology nodes. If you have the synthesis tool, logic synthesis tool, once you have the different technology libraries, you can use the same RTL code and implement, or the Verilog code and implement that in, let's say, 7 nanometer technology. I can also take the same Verilog code and implement it in 5 nanometer technology node. So it is totally, you can seamlessly use the same code and implement it in different technology nodes, right? So that's the advantages that you have with synthesis. Coming to the goals, right? Like every chip has some goals. The first one is maximizing performance. So that is nothing but meeting your frequency. So I don't know how far you people remember the phones that came out in the year like 2003, 2004. And if you see the mobile phones that we are using right now, they've grown like 10 times faster, right? Same with our computers as well. They used to be pretty slow, and nowadays the systems that we are using are pretty faster. It's all because of the leverage that we get using the lower technology nodes or the kind of gates. Also, we are able to hit higher clock frequencies. That is nothing but improving our performance. So the clock frequency for the synchronous systems and throughput for the asynchronous systems. So using this, we are able to increase the performance. And one of the goal for synthesis is to meet the performance. Let's say I'm saying that this chip has to work at 2 gigahertz. One of my that is one of the constraint that I give to the synthesis tools, and I have to meet that constraint, the performance constraint, right? The other thing is minimize the area. We see that with the technology nodes, the chip sizes are decreasing pretty faster, and we are able to get more computation within a smaller device itself. So what we were able to do with a computer 15 years back, we were able to do the same thing with our phones in our hand right now. So it's all possible because like we are able to minimize the area of the chips using the latest technology nodes and everything, right? So that is one of the major goal. The third major goal is the power. As you keep increasing the frequency, what happens? Your overall power, because your computation is happening so fast that the power generated will also be higher, right? So you have to reduce the power as well. And along with the power, the heat gets generated too. That is also an important aspect to address. So when it comes to the power, you have different types of power: dynamic power, leakage power. This will get into the details like later what these different types of power are. But we have to address these. So these are the three main, like, it's called PPA, performance, power, area. Generally, PPA is the three major goals for any chip designer. So coming to the basic synthesis flow, I mean, I just explained that in brief, as in like what are the different steps, but I'll just delve a little bit deeper, right, into what happens in each stage. So the synthesis flow happens like this. First is the syntax analysis. So you take your RTL and do a syntax analysis, whether there are any bugs or any mistakes in the RTL code that is written and all that, right? Before you even take it forward, you first look for the syntax errors or syntax issues. Then you do the elaboration. Elaboration is the place where you also read in your .libs. You take your .libs and do the elaboration. And then after the elaboration, you do an inference or a high-level optimization using the SDC constraints. Then you do the technology mapping. I've shown scan insertion here, saying that scan insertion happens there, but not necessarily. Like I said, some people do scan insertion after the whole synthesis flow is done. It depends on company to company. It changes from company to company. Some people do it in between the synthesis flow. Some people do it after the synthesis is done. So it varies. So after the technology mapping is done, then post-mapping optimization happens. And after the optimization, you write out your reports and analysis. Also, you also write out your netlist, SDC, and scanf that we saw in the previous. Good. Okay. So like I said, the first syntax analysis, you look for the syntax errors. That's the main thing. The next step is the elaboration, right? So what happens in an elaboration? So it reads through the RTL code, then it converts the RTL into the Boolean structure. So that is the whole reason why I explained about the Boolean logic previously. I mean, the Boolean algebra, right? So why is this important? It's important because that's what happens in the elaboration. It takes those RTL gates and it not RTL gates. It takes the RTL code and convert that into a Boolean structure, right? And if there is any dead code, or if there is any, sometimes, I mean, you have these modules, right? And you have some code written within the module and end module. Sometimes I might define an empty module thinking, okay, later I might add something to it. But empty module is useless, right? As long as it is not used, it is useless to have it in the Verilog code. So what happens? The synthesis tool also gets rid of that unused modules or the unused Verilog code as part of the elaboration itself. And the next comes the inference and the high-level optimization. So every tool, right, like they have internal gates called as a generic gates. So it has nothing to do with your technology library or anything. So it takes that Verilog code and maps to generic gates, which are like the internal gates for the tool. Thereby, it tries to reduce the number of gates that you have in the design itself during the high-level optimization. Once it converts that into a generic gates, then the post-mapping optimization happens. So this is where it actually converts all those generic gates into your technology gates, the inverter, AND gate, OR gate, or the complex combinational gates and everything. And what happens during the post-mapping optimization? It tries to meet your timing, which is nothing but your frequency, performance, right? It tries to reduce the overall area. It tries to reduce the power. It tries to reduce the number of gates. Reducing number of gates is nothing but reducing your power and reducing your area, right? So it is directly implied. And it will also see that you're meeting your SDC timing constraints. So once this is all done, it dumps out the final reports for analysis. So just because you have constraints doesn't mean that tool will definitely meet it, right? It could come out with some violations or some issues saying that, okay, I'm not able to meet these constraints. So as an engineer, as a census engineer, it is our responsibility to go into those reports and see what are the issues. If there is more power, like what is causing more power? If it is not able to meet the performance, why is it not able to meet the performance and all that, right? So, okay, before I go deeper, I mean, before I go to the next slide, right? Maybe I'll tell you. So this logical synthesis previously used to happen in something called as a wire load model. Wire load model is nothing but, I mean, it's called as a zero wire load model. So you don't have any physical information of wire or anything for you to, I mean, it's basically all the wire load and everything is considered as a zero delay. Only the gate delays are taken into account. But these days, the designs have become so complex that you have to do a physical census. Physical census is where you take into account even the physical location of the cells, your wire load, everything, right? So these are some changes that happen to the census flow over a period of time, and with the design maturing and with the technology nodes and all that. Okay, so I would just like to have a small interactive session. I mean, this is, I mean, I just don't want to keep asking whether you guys were on when we discussed about the basic census flow.
Yes.
On, like I said, this is a small interactive session wherein I want your inputs, or I just want to see how you guys think through this, right? So this is a doorbell system, and it consists of a sensor that detects when the door is open, right? So when the door is open, the doorbell rings and an LED indicator turns on. It's a combination of AND or NOT gates to control the doorbell and LED. It's a simple system. What you to do is optimize this doorbell circuit using logical census techniques to achieve the following. One is the performance, right? Minimize the delay between opening the door and doorbell ringing. As in, as soon as a person opens the doorbell rings, right? So I want to reduce the time between the door and doorbell ringing. That is nothing but your performance, correct? So that is how fast the doorbell rings after the door is open. So coming to the power, right? Ensure that the circuit consumes as little power as possible when the door is closed. You all would have used the logic gates to light up an LED indicator and all that, right? So it's as simple as that. How logic sensors can be used here. I'm just asking, I mean, this is just a scenario. I just want you to think through this, right? So how do you design such a circuit, correct? Like using an AND or a NOT gates. PPA, which is the power, performance, and the area. Of course, here area is not a matter because like it's a pretty small, like as in you have an AND or a NOT gates. So performance and the power efficiency is what I'm looking into. So how can you like just think, increase the performance, or improve the performance, or like reduce the power, right? Like I'll try to explain. I mean, if you guys can't think through, I'll try to explain like how do you improve the performance, right? So in this case, changing the logic structure, the way you use the and, or, and not gates to design, right? So that itself can be optimized. So rather than using a sequential logic to capture the data and only in the next clock cycle enabling the data, right? I can use a parallel logic to reduce the delay. Instead of sequential, I'll just use a parallel logic, right? Parallelly, I'll keep sending the data. And the second way is to use the faster gates. The AND gate, there will be generally different flavors. For each technology node, there will be different flavors of AND gate, different flavors of OR gate, NOT gates, right? So there'll be a slower gate, there'll be a faster gate. So by changing them to faster gates, I can also see that I am meeting my performance, correct? So that there'll be a little less lag between when the door is open and when the doorbell rings, right? Coming to the power, turned on always, but that consumes power. Instead, I can make the LED power on only when the doorbell rings. Open, but only when the doorbell rings. That way, I'm reducing the power as well. Just a couple of ways. I mean, I just wanted you guys to think through like a small scenario as to how we can improve the things. So whatever thought process we have just done is nothing but a logical synthesis in a smaller format. That is what this logical synthesis tool does in a wider format. Future trends, right? So logical synthesis, we have been doing logical synthesis for quite a long, and the machine concepts were used in the logical synthesis tools for very long. But as you all know, the AI and machine learning has advanced over the last 2-3 years, right? And the tools that for logical synthesis are also incorporating all these AI and machine learning into them, and the tools have become very smart. So using these tools, you would be seeing a huge performance. Probably, since you may not be aware of how tools were like 10 years back or so, but since I've used the tools 10 years back and I'm using the tools right now, I know like how the tools have changed over the period, and it's a significant change, I should say. Conclude my presentation here. We have barely scratched the surface of logical synthesis today. So we have seen how the logical synthesis transforms the abstract design into a tangible circuits, and how you can optimize your power, performance, and area. Right. I hope this glimpse has sparked some curiosity in you guys.
Hello, sir. Hello.
Group.
I have some small doubts, sir, in synthesis flow.
Guru, you can ask.
Hello.
Ask your doubt. Ask your doubt.
Group.
I have doubt in synthesis flow, sir. Small doubt. User is having the deco. Please open the slide, sir.
Yeah. Let me go there.
In this state reduction and remove any dead codes means, sir, it will remove the any unwanted codes, sir.
The synthesis tool optimizes a code, right? You might
Yes,
have
sir.
written a code, but it optimizes that code as well. So like I just told you, like if I wrote an empty module thinking that, okay, maybe as I improve, or if I want to add new features in the chip later, I'll just put an empty code initially, thinking later on I'll add it. But when I'm synthesizing, it is of no use, right? It does not do any function. Such kind of dead code. I just gave you an example of a dead code, which is not really used. State reduction. About the state machines and all, right? The finite state machines. When you have these state machines, like you try to minimize the number of states in those FSM or the finite state machines, right? End up using very few gates in order to realize that particular finite state machine. State reduction. The state machines, the Mealy Moore.
Okay, sir.
The synthesis tool will try to reduce those states. That way you will also end up using less number of gates to realize those states. Am I clear? Guru, did that answer your question?
Okay, sir. Thank you.
So anyone else, any doubt? Anyone else, any doubt? Anyone have any doubt?
Sir, could you please
Feel free
send
to
this,
ask.
Yes, okay, that time.
could you send this PPT in our WhatsApp channel?
No, this is for the PMA students only. This is for the you can WhatsApp me. I will share to you. Fine, you can personally WhatsApp.
Okay, sir.
Okay. Anyone else? Any doubt? Okay, then. So I guess we can end the session, sir. So thank you, sir. Thank you so much, sir. Thank you. Thank you.
And thank you everyone for joining me today.